remember, like in the last lecture, what we wrote is the delta function of SU2 with the Peter-Val theorem. What we said is that any function of SU2, we can expand it in terms of sum of the spins and then the representation matrices of SU2. So we can do the same thing here. We have a delta function. This delta function is a function of SU2, so we can expand it in terms of representations of SU2. This is just saying that this delta function, we can write this down as a sum over all the spins. So now we have a group element, the H, for all the faces. So this means that we, with the Peter-Val theorem, so this Fourier transform on the group, we're going to have spins on all the faces. And the sum of all the spins, we have a product over all the faces of the dimension. This is the dimension of the spin JF SU2 representation. Then we have a product of the edges. This can seem like really big and complicated, but if you think about it, it's not that complicated. So you see that this so I didn't touch this integral here. So this one is still here again. The only thing that I did is expand this delta function on SU2 with the Peter-Val theorem that we wrote last week. And so this tells you that delta function on SU2 is the sum over all the spins, and a product, I have a product over the faces. I have this product over the faces of all the representations, and then I have a product over the faces of the trace of the representation matrices. This is the trace of these SU2 group elements. Now the last thing to do to get to the result is to now do this integral over the group elements. And now the other thing that I did is to write down the holonomy around the face with its definition. The definition was that the holonomy around the face is the product of the holonomies around the edges going around the face. It's just this definition. And now we can integrate over SU2 here. This is where we have to be very careful now and understand what is happening. Because how do we do this integral now? I want to look at what happens, and the result is going to follow immediately. Now you see that these integrals, they are completely, they're not redundant, but we're integrating over group elements that are shared by many of these group elements are shared by the same face. And what this means is that, remember what a face is and what these E are. So these E's are dual to the triangles, and the faces are dual to the links. But see that if I choose like tetrahedrons like this, the triangles are bounded by 3 links. So whenever I have a triangle here, so a triangular face, I have 6 links around. So imagine that I have a tetrahedron like this. So I have this space, this triangle here, this triangle with the tetrahedron here, this one. But this triangle is bounded by 3 links. So you have the link L1, the link L2, and the link L3. So what I have to worry about is how many faces share the same element E. Because see here, I'm taking a product over the faces, I'm integrating over the elements HE. But some of these faces, like for example 2 different faces, they share the same element E. This just means that in the dual complex, the faces they meet at the same edge E. But this means that in this picture, which is much more clear, the same 3 different links, they can bound the same triangle. I can have like 2 different links that don't bound the same triangle. I can have this link here and the link in another tetrahedron, so these they don't interact. But I can have this link here, and this link here, and this link here, and these 3 links they belong to the same triangle here. And so this means that what I have to worry about, if I attempt to rearrange this, we could rearrange this and see that this integral is going essentially to feature something of this form. We need to integrate over THE over SU2. And then we could write this trace in terms of representation matrices, for example. We'll do this. We have a group element G. So now what I put here is like 3 different spins. And the reason for which I put 3 different spins with the same group element here is that the spins are assigned to the faces. So I have 3 different spins because the faces are dual to the links. So you can imagine that you have a face here dual to this link, a face dual to this link, and a face dual to this link. So these faces are labeled by spins, so we can think of the links as being labeled by spins. So in this formula, what is going to happen all over again, in this formula, are integrals of this form. So integrals of our representation matrices for the same group element 3 times. And why for the same group element? Because this triangle is bounded by the same 3 group elements. This triangle here is bounded also by the same 3 group elements. And so what we said last time, we saw exactly this integral. We saw it when we constructed the gauge invariant Hilbert space. And what we said is that this integral can be computed, and essentially if you have 3 representation, the outcome of this computation is just a product, so a contraction of two intertwiners. So one intertwiner and these 2. And what do these intertwiners do? They intertwine between the 3 representations J1, J2, J3. So you can think of this as assigning, once I do this integral, I assign to all the triangles of the tetrahedron, I assign the intertwiners. So I have like four triangles here, bounding the tetrahedron, and to all these triangles I assign an intertwiner. And what this intertwiner is doing, it's intertwining between the 3 representation coloring planes. But this looks a bit like, looks maybe really weird and don't really see what happens, but let me write this again. I have this tetrahedron here. And you see that you have a certain group element here, here, and here. And then once I perform this integral, for all of these triangles, I get an intertwiner. I get one here, one in this face, and one face on the back, like one. So this means that the tetrahedron is a contraction of 4 intertwiners. So this tetrahedron, if you looked at the index structure of this tetrahedron, would be just a contraction of all these 4 intertwiners. And these 4 intertwiners, they are labeled by spins, of course. And which spins label these intertwiners? So it's the 6 spins that are the links of the tetrahedron. So I have a spin here, J1, J2, one on this link, J3, one here, J4, here I have J5, and here I have J6. So if we have a tetrahedron, we have a spin on all of the links, so we have 6 spins, and we have an intertwiner on all of the triangles. So we have 4 intertwiners. And so what does this correspond to mathematically? A contraction of 4 intertwiners like this. You see that all these intertwiners, they are 3-valent. They are 3-valent because they intertwine between 3 spins. If you had chosen a more complicated discretization, so not tetrahedral but cubes, for example, here we would have, for example, 4 group elements, or 5 or 6. But here we would have a sum over the dimension of this intertwiner space. But when it's 3-dimensional, the intertwiner space is only 1-dimensional. So there is no sum, there's only a unique 3-valent intertwiner. So we have 4 intertwiners contracted in 6 spins. And so what this means, from the group theoretical point of view, this is what we call the 6J symbol. So we write it like this, and this 6J, and also write it like this if you want. J3, J4, J5, J6. What this computation does essentially is that you can completely simplify now this discrete path integral and write it as so a sum over all the spins, now a product over all the faces of this face amplitude, 2jf plus 1, and then a product over all the vertices, because remember now that the tetrahedron is just dual to a vertex, so you have a sum over all the vertices, and what is the weight, the amplitude that I assign to the vertices is this 6J symbol. This means that, think again of the vertex as being dual to tetrahedron. For all the tetrahedron, I have 6 spins that are coloring the links of the tetrahedron. And these 6 spins, they define this 6J symbol. And mathematically, this 6J symbol is the contraction of 4 3-valent intertwiners. This is contraction of 4 So in like books on angular momentum, we can find expression for this 6J symbol. They're just like very just messy functions of all the spins. It's completely not relevant. But we never in fact write them down. I think nobody working on this knows by hand what this expression is, because it's completely, at this point it's completely useless. But we just have to see is like, think about this formula a little bit and see that once we integrate over its group elements, some of these group elements are shared by many faces. So that for each face, we have this product over this HE. What we're saying is that for some faces, many faces share the same group element, HE. So when we put them together and integrate them 3 by 3 like this, whenever we integrate 3 of them together, we get this 3-valent intertwiner. And each of these 3-valent intertwiner is associated to a triangle of the tetrahedron. And then once we contract them together, we get these 6J symbols. So at the end of the day, the result is this one. We computed this discrete path integral on the discretized manifold. And what we have is exactly the form of a spin-fold model. We have exactly this form here. We have a product over faces of phase amplitudes. And this phase amplitude is just the dimension of the SU2 representation. And then the product over the vertices of the weight. And this weight is a 6J symbol. And there is a very precise sense in which this is exactly the path integral for a 3-dimensional gravity. And what can be shown is that because the theory is topological, so because there are no local degrees of freedom, by choosing a triangulation, we're not throwing away any degrees of freedom. So we're not losing any information. This means that, I'm writing this very formally, but this is really a true statement. If you write this path integral, writing this on a triangulation, it's the same thing as writing down on the full manifold. So if you choose one triangulation and choose another one, we compute this thing, it gives the same result. And this is why mathematicians were the first people to write down the spin-fold models. Because what this computes is a topological invariant. This means that if you choose a manifold with a given topology, then you can choose any discretization. You can choose the simplest one, just one tetrahedron, for example, and this is just a number. You can compute this, and this gives you a number, a finite number. And this number is a topological invariant. So it's only sensitive to the topology of the manifold, and not to any other underlying thing that you choose. It's not sensitive at all to discretization, because the theory is topological. So once you take it, you discretize it, you're not throwing away any degrees of freedom. You capture the entire physics of the theory. So in this sense, using one discretization or another one, it's completely equivalent. So you can write that this is really the path integral for the full manifold. the story in 3 dimensions. So in 3 dimensions, we can show explicitly that the path integral for 3D gravity takes exactly the form of a spin-fold model. And now what we want to do is do the same thing in 4 dimensions. We want to take the structure and see how in 4 dimensions we can reproduce the same thing. Well, let's do a break.
So let's come back in 15 minutes.